welcome back to the Women LeetCode Python tracks. This is the LeetCode study group section, I think 7, 8. I should remember.
Yeah, 7.
Yay, 7. So for those who just joined back, welcome back. First time, this is the first time for you. My name is Karen. I'm one of the moderators for this series. And we have Chethana here, who is the instructor of the series. Off you go, Chethana.
Thank you so much, Karen. Welcome back, everybody. We had a little bit of a break. Hope you all had a really good holiday. So let's get back into coding. So today's agenda is an introduction to backtracking, which is the pattern that we're going to be talking about. And the problem we've chosen is subsets. So very common / popular backtracking problem. And we have, for the deep dive, we would discuss the problem, talk about some test cases, time and space complexity, live coding, and then where to go from there, and then our Q&A at the end, or as in when you have questions in the chat as well. Awesome. So backtracking. Let's do a quick intro about it before we actually start, right? Backtracking is a general algorithm that is used to find solutions to computational problems. And you will have, probably when you type backtracking on Google, Wikipedia, so many websites, they would have specific ways to describe backtracking. And this particular line is like a combination of everything that we've seen, learned, and read. So what exactly does this mean, right? Like, what are these solutions and how do we find these solutions? And how do we actually, what kind of algorithm is this? Like, do we use iteration? Do we use recursion? Basically, you sort of incrementally add to each solution, to a solution at a particular level, or recursion level, or iteration. And at the end, and at each turn, you make a couple of decisions. That is the making decisions part. That is what differentiates backtracking from other algorithms. Why do we make these decisions, and what are these decisions based on, and stuff like that. We will talk about them as we go on. For now, let's just go with the flow, and we'll break it down as we go. Okay, so we were talking about solutions, right? We find solutions to problems. Okay, that seems to be the goal of every algorithm out there. How do we do it? At each iteration or recursion level, you would have already had, because this is recursion, this is mostly done using recursion. Recursion just makes algorithms like these easier to code out. For some reason, this DFS, BFS, all of these algorithms, it's just better if you do it recursively, because you don't have to think of every single iteration. You just, like we were speaking before with recursion, you just trust that it will work. The logic, if it works for one specific subcase, it will work for the rest of them. So at every recursion level, you will take the solution that you already have at that point, and you would extend it. And you would also have another case, which is like a termination or like an ending case for backtracking, like a base case. Is the current solution the right solution, or one of the right solutions? If so, then you record it somewhere. You make sure that the particular solution you got to is not lost. So you record it somewhere. If it's not, okay, then what do I do to get to the right solution? I take the current element, or I take whatever path I am currently, I will append it to the solution that was already there from the previous iteration. So from a previous iteration to now, you take whatever current element you're at, you append it, and then that's what I meant by you extend it somehow, and then you continue with your algorithm. Super vague, right? Like, oh, what's she talking about? So like we'll look into it in a second. Okay, with what we spoke about, and in general, if you look at any backtracking problem, like all over the internet, when you're studying for an interview, you will have some kind of template that people follow. Like you see like some kind of way in which these kinds of problems are solved. Like maybe so according to me, this is like my view of what I've seen and like mixed with what I've learned. So let's break it down, right? So you're finding a solution, right? Which is find solution. That is your main function, or like if you're finding a bunch of subsets, the find solution would be generate subsets, okay? And what do you do within it, right? You will always have like a backtrack component within it, a backtrack function within it. So within find solution, you will call this backtrack function, you will call it with some kind of like a base condition situation. Like if you need to construct a string or something, like a crossword puzzle or something like that, and you need a string, right? You'll pass in an empty string. If you have like an array kind of situation where you need to append elements to an array, and like that, your solution, it depends on your solution and what kind of solution you want. So you have to call backtrack with your empty, with whatever your base case is. Starting index, empty string, empty like empty array, etc. And what exactly happens within backtrack? The reason I've mentioned it as current partial solution and current index is because what we are at, the solution that we are at every iteration, we don't know if it's whole, if it's like a full solution or a partial solution or not at all a solution. You don't know any of these three things. So we just know that if we haven't discarded this is maybe a partial solution. So that's what we're checking here, right? If we start off by checking if this current partial solution is indeed a solution. If it is, then we record it somewhere, or like count it somewhere or something like that, and then we return. If it isn't, then whatever element we are at, or whatever letter or character we're at, basically the whatever is at current index or the current position, we will add it to our current partial solution. Or if it's like a game, or like that n queens problem, or like a chess, chessboard, chess kind of move situation. I don't know what I even said. Chess kind of move situation, but you get what I mean. If you're making a move while playing chess, you make the move, like all of these things, like like what I'm trying to say here is add that whatever you are at into your current partial solution, right? And then you run backtrack on it again. With that extended current partial solution, I didn't have space because I was like making up my own words, so I just wrote it as SOLN, but solution. And then you increment in this case, since I wrote it as current index, I'm going to increment it by 1. If not, I would just say like increment the position, like, or maybe like a count or something like that. I would increment it by 1, or I would find a way to consider the next portion of the search space. That's what I mean. Oh, I should have yeah, but it's too long to fit there. Any way to move to the next portion of the search space, and then I would run backtrack on that, right? In the end, somewhere it's gonna hit that, if any point down the path is a solution, then you're going to like figure that out and add it to your solution set. And then you make that move, you add it to your current partial solution. Sometimes in some problems, you'll remove it from the current partial solution, and then you'll do another backtrack on it. It really, really depends. Sometimes you would you would just do the first adding to it, and then like yeah, actually you need to make decisions. That's where backtracking differs from other things. So you either add it, remove it, you do both, try to figure out what's going on, right? So this is like a kind of a template that I've seen in problems. And this one, it definitely depends on like what kind of solution you're expecting, what kind of input you're passing, what is your search space? Is it just like an array or like a string, or what is it, right? Like all of that, it depends on that, but generalized it. Great. So now that we've spoken a little bit about backtracking, yeah, we're actually going to talk about that here. So when and where do we use it? How do you know if you want to use this or not? Yeah. So if you have like a whole search space, and you would need to like explore that entire search space to see which one works, which one doesn't work, which ones work, which ones don't work. And, you sort of build your way to it. And this sort of thing you would find in most combinations problems, permutations problems, and then like when you have to find when there's a possibility for you to find all of something and pick and choose from that. I think I've also mentioned it in the next steps to go from here slide, but you could start working on problems like subsets, all of subsets. We're going to talk about the subsets, original subsets problem here, but combination sum, and then those variations on LeetCode, and then you have you also have permutations where you can like, there's a problem called permutations, and it's basically whenever you see like find like some kind of path where you like, when you see a problem, you're like, okay, I have to go through everything to find answers to this particular question. I can't skip anything. if you need to do that, the input isn't in a good way, or like in like a pruned kind of way, then you have to use it. Like this is very slow brute force. It's like brute force literally, but sometimes you just have to go with it. You'd see for subsets that this particular time and space complexity with backtracking works better. Seems to work like the fastest compared to many other. I think even the other solutions that people talk about for subsets, it's pretty much the same thing. So yeah, we're gonna deal with that now. Okay, so it's a very short intro because there's not much to like. There is some stuff to unpack, but it's not like if you choose a sliding window or something like that, like if you choose a pattern like that, you have a lot of like steps to think about, like stuff like that. Here, if you just see like, when you see like, it would also help to start off with searching by backtracking tag on LeetCode, or even in Google. There's like a lot of like, even in search, there's a lot of people, they would put out lists for each algorithm that you can tackle. And I think there are some GitHub repos as well. I'm not sure why I'm pausing here to talk about all of that, but what I want to say is it's a pretty small intro, but you like when we talk about the iterations of subsets, like the actual examples, it may get a little bit taxing. So yeah, with that, I'm going to I think I'll take a quick water break before we actually start subsets. It's a very it came sooner this time, Karen, but yeah.
No worries. It's all good. It's all good. So yeah, no, take a quick break, take a quick break. So for those of you who I see couple first time joiner here, so I'm just gonna, while our channel is taking a break, I'm gonna go walk through how we doing the live coding section. It's a little bit different than the other study group series. So I am posting a link on the chat button right now. So in short, our live coding session will be done on REPL. REPL is a website where you similar to the Google Colab. You can post, like you can share your code there, so people can just see, and then like you can also like get it as like a cloud driver and keep all your coding stuff there. So a little bit of walkthrough in case this is the first time joining. First of all, you need to sign up for an account. It's free. So we encourage you to sign up for one in case you don't have one yet. If you want to see, so the second thing, in case you joined it already, fork the repo on the top right corner. Just fork repo, and then you will get the most updated material on for this, especially for this LeetCode study group. So after you fork your repo, you can go back to the link I sent you. So Chethana, the material Chethana will be talking about, where you can see them. So on the center, a little bit left, on the center, a little bit left screen, there's a button for Show Files. Click it, and then you will see all the past coding we've done, and also the most recent one, which is backtracking. So just click the backtracking and click the success.py, and you will be seeing the code where Chethana will be demonstrating. So there's a little bit of intro of this repo and live coding section. Anyone can I get a B or P just to check if everyone is okay with this before we move on? Yes, you click on the success.py and you will see the code. Yes. That's good. That's good. Good. Awesome. So in case you guys don't have the repo account yet, but like want to know what Chethana is talking about, I just post the actual LeetCode link on the chat button. So Chethana will be covering the exact same problem. So you can, if you don't have a repo account, you can also fill it in the LeetCode as well. So it's you guys' choice. So any questions, just let us know, like, anytime, and then like I can definitely help you with that. So I guess that's all. Chethana, you ready?
Yep, I am. Thank you so much, Karen. Yeah, so and also if you see the word pass inside the function, that if you're already on it, it means I haven't like I would code it out at the end, like in the actual session, like right now, and you could just refresh the REPL, right, Karen, and then they would be able to see it. Yeah, so yeah, we'll just go as we go. I don't know if that made sense, but just yeah, awesome. So subsets, great. Let's just read through the problem statement, and then try to like unpack what's written here, right? So given an integer array nums of unique elements, return all possible subsets, in brackets, in parentheses, the power set. The solution set must not contain duplicate subsets. Return the solution in any order. Ooh, okay. So a couple of things, right? Couple of things to unpack if I can get my cursor here. Okay. What is a subset? Let's go back. Given an integer array, which is unique, it's called nums, you return all possible subsets. And to add to that, they're saying something called a power set. Okay, so what is a subset? In general, it's a subset consists of elements contained within the set, or like in this case, nums. And we can still call nums, even though they've mentioned it as an array, it is a set, right? Because it has unique elements. So let's just go with that. And for example, if your nums is 1, 2, what are the subsets there? One thing about empty subsets, I will talk about it more in the actual subsets, like the REPL, but in general, if you have any, there are like proofs for this, like mathematical proofs for this online everywhere. But for any non-empty subset, any non-empty set, the empty set and itself are subsets of it. What does that mean, right? If you have 1, 2, this is non-empty, like you have 2 elements in it. For 1, 2, 1, 2 is a subset of it because there are elements contained within it. And the empty set is also, it is also a subset of this set. Again, there are like, this is something universal that like mathematicians have proved. I'm not gonna get into those details now, but I did put out a link in the REPL for it. But that's essentially a subset. Okay, so like what now? We had another weird thing to unpack, right? Like, what is this power set? It is a set of all subsets within that set. In this case, it's nums. I just generalized it and called it set S, but it is basically every possible combination or every possible subset that you can derive from your input array. So that's what we're gonna find out here. Like we said, like backtracking, you just explore, like exhaust the entire search space. Our entire search space is nums, right? So that is our scope. Okay, so the input, like what is our input, what is our output, that kind of situation. So our input is an array called nums. Like, for example, in this case, we're mostly going to be doing this example, which contains 3 elements, 1, 2, and 3. And then our output is the power set of nums, every single, a set of all subsets within nums. And then the solution, it can be in any order. That is good, right? Like we can, anytime we visit it, anytime we figure out that something is a solution, we just add it to our solution set. A solution set. And then you should not have any duplicates. I think that would get handled with how we with our kind of backtracking solution. But for now, these are all of those things that you can get from that from your problem statement. And a couple of other questions, like, can you think of anything which we're kind of missing? Any questions that come to mind? And also, if you're able to follow so far, could you send a B or a thumbs up or something in chat? Awesome. Oh, okay. So those are just examples, like separate examples. Like this is our input array. And we're going to be doing this in the REPL that we sent initially, because I've already set that up to have like my thought process on how to explain it, and like examples, and like we've been following this thing of like maintaining all of our solutions and whatever problem we pick within that particular REPL. If you look at like you'd have like the past solutions and stuff. Okay. Sonia, like, were you able to, like, did you sign up? Which part are you stuck at? Oh, okay, you are in your REPL. Oh, okay, we'll get to that in just a second. But before that, is there any input related questions? Like, like, do you think that like can nums be empty? That kind of stuff. If you have any of those kinds of input related questions, just drop it in the chat. Otherwise, we can, I think, move forward. But in my head, when I saw this, I thought, okay, you're saying you have like an integer array called nums. Like, can nums? Yeah, the output is like a bunch of subsets of the input. Like if you look at this example that I have here, which says 1, 2, the empty set. Oh, I think I didn't walk through that. I'm so sorry. So like the empty set is a subset of that, of whatever, of 1, 2. 1 is also a subset of it. 2 is also a subset of it. 1, 2 is also a subset of it. So these are all the subsets of 1, 2. Awesome. Okay. And then I was wondering if nums can be, if nums is like, yeah, awesome. So I was wondering if nums is empty, like, what happens if nums is empty? What do we return? If you have an empty, for a non-empty subset, its subsets are definitely itself and the empty set and other combinations within it. So for an empty subset, like just have you have like an empty nums, then a subset of that would just be the empty set, like and you would just return that maybe. So I think other than that, nums does not have duplicates, so we're good because it's a set, right? And then as you can see, the subsets can be returned in any order within, I mean, the order of subsets within the result solution. It doesn't matter. Great. So now let's code, right? And hopefully, like, because I took so long, I think we haven't, we won't have, yeah, I'm just gonna go ahead and get in. I think I forgot midway what I was trying to say, and okay. So this is where we were. I hope everybody can see my screen and the font and stuff. I hope that's okay as well. This is the largest font here, and I think it should be okay. If it's okay, please thumbs up or something in chat, if possible. Great. Awesome. Thank you so much. Okay, so basically we have all of these other like folders and stuff that are within our files, and then the backtracking one is this, it's subsets. So let's talk about that now. And I also have like, so basically for each folder, or from each folder, I sort of run those run those particular functions that I write in this main.py, which is our entry point. So here I just imported the stuff and wrote down some examples, mostly from like LeetCode and stuff like that. We could do like other examples if you have in the chat. I think it's probably simple. Like it's just like it shouldn't have duplicates. It should just be like a bunch of integers. And yeah, I think integers could mean positive and negative, but yeah. Great. So let's go into subsets. Subsets.py. Couple of examples, because we had touched base on this 1, 2, 3 situation, this particular number combination. So when you take the subsets of this, the first one would be the empty one, and then you'd have 1, 2, 3, and then you could have 1, 2 together, you could have 1, 3 together, and then you could have 2, 3 together, and then you could have 1, 2, 3 as well, right? Because empty and itself are also subsets. So this primarily we're going to be talking about this example more because it seems like a good size to talk about, and not too much so that it gets really redundant. And if you have nums of 0, then again, like empty set itself, like I've written, and this is for that explanation where I was talking about like those proofs and stuff that I was mentioning. I think you can get some answers from here, and basically whatever we discussed is like I've written it out again. Okay, so now that we've looked at a couple of examples, let's talk about some approaches. The first one is something called cascading. It was on LeetCode, but mostly, I think it's even in all of these computer science textbooks. If somebody says backtracking, the first thing they say is, oh, generate all subsets. Like subsets is like one of those kinds of problems. So we naturally move into backtracking, and I don't think there's anything faster than backtracking for this. But for the sake of completeness, I wanted to add this solution as well because I thought it was really intuitive. So and we wouldn't be coding this one out, but we would be coding the backtracking solution out. So we have nums as 1, 2, and 3. Okay, and basically what this approach is you take each of your each of the numbers within within nums, and then you add it to your solution set. You add that number by itself to the solution set, and if there's any other combination, any other combination that's already there, you add this to those combinations, and then you make a new set. You make a new subset with it. For example, you'll always start with your empty set, right? And then your pointer probably would be at 1. Your index would be at 1. So you would add you would add 1 to it, and whatever existing combination was this, you could add 1 again to it, but again, that's a duplicate set subset, right? So you wouldn't. So that's it. This is at this point when you've just seen 1, this is your solution set at that point. Great. What about when you add 2, right? What we spoke about, what we would actually do, we would take 2, we would add it to our solution set. We've added it. And then if there's any other combination or anything that already exists, you would add this to that. So you already had 1, right? So you'd create 1, 2, but this would be like a new combination. Like you wouldn't override this and lose the previous existing subset that we already generated. And then now 2 is completed because we finished adding 2 to all of those combinations. Now we have 3. You add the number 3, that is already added, right? And then what other subsets do you have that you can add 3 to? Like you have 1, you have 2, you have 1 comma 2, right? So you will add 3 to this 1 subset, making it 1 3. You will add 3 to this 2 subset, making it 2 3. And you would have you would add 3 into this 1 2 subset, making it 1 2 3. So this is this method. It's still pretty good. It's really intuitive, but because for the sake of how we're going to do this, and because backtracking is more like prevalent for this, we're going to discuss that now. Okay, so nums, like so far are we good? Like are we understanding the like what our input is, what our output is, like what we need to find? Maybe like, are you maybe getting stuck somewhere in any of those things? So drop it in the chat. Otherwise, let's keep going. So nums is 1 2 3 again. Okay. We now have to think about, okay, how do you create each of these subsets? Like we were talking about the same thing before as well. Like we were saying, oh, okay, well, we're going to do it like this, we're going to do it like that. But how exactly is a subset created when we're going to do it with the template we had in mind for backtracking, right? Like we take something, we add to it, and then we check if that works, and like that whole thing. How do we make sure? And we also spoke about decisions that we have to make when you pick an element in backtracking. What are these decisions, right? So for each element, if you actually think about it, you would either pick, like if you notice here, you have 2 3, right? But you don't have the 1. You have 1 3, but you don't have the 2. So and you have the 1. So you just you notice this pattern where you either have something or you don't, like where you like make decisions to either pick the element or not, right? So if you look at this, you either choose one or you don't choose one. And then what would you do after that? So you would run backtrack for the rest of your input array. And for each turn, for each of those iterations, you would either choose that number or not choose that number. If you choose it, what happens? And what happens is you running backtrack and finding out where it ends, like which solution it yields. Right. And there's no possibility of it doing like a duplicate solution with the way we've been doing it, because you're taking something, and then with that something you're running a recursive function on it, and then you're removing that thing out, and then you're running the recursive function on it. So like it's bound to yield, sorry, did I say that right? Okay. It's gonna yield unique combinations, and yeah, so let's actually talk about it again. We're going to keep talking about it, and by the end, when you come to the actual coding part, it would be like, oh, okay, it's just this. So let's do that. I'm saying like a lot of times. I think it's like my filler or something, but thank you for bearing with it. Again, so run. You start off. How do you start off, right? Like you need to have an entry into backtrack somehow, right? That backtrack function. You would start by setting your current index to 0 initially, okay? And when do you know you don't have? When do you know you've reached a solution, right? Like the solution testing case, solution testing, or termination case. If your current index, if it's greater than or equal to the length of the length of numbers. Like, for example, you're initially here, right? You're passing 0 as your initial place to start the backtrack. So if it goes here, right? For any recursive level, it goes here. You don't really, like, you can't really go beyond that. This is like a base case, right? So in that case, you just append whatever you have as your current subset. You append it, like you don't just append it. You make a copy of that current subset. We'll talk about making that copy. Like, why do we need to make that copy? Because ideally you would take the same current subset and you would keep modifying it, right? Like the same variable, you would add to it, you would remove from it, and then you'd append to your main solution. You'd append it to your main solution. And like, if you do that, then that current subset is going to be heavily mutated. Like, it's going to be so changed. And every single time as you add and delete and stuff like that, it's the reference of the current subset that you have in your actual solution set is going to change, right? And you wouldn't have a record of your unique subset at that particular depth or level anywhere. You just have like a mess of whatever your last iteration left for you, that would be in your solution set. So that's something, and you would also end up with a lot of duplicates and stuff. So that you have to keep that in mind. You just make, I think you can make a deep copy or just like a shallow copy. I think that's what we're going to make. Yeah, I'm thinking of the differences. I think one makes like a clean slate copy, whereas the other one, yeah, I'm not gonna go into that, but when you make a new copy, you can also create like a temp array and add all of your like the current subset stuff into your temp array and append that temp array into your solution set. You can do anything, but you just have to make sure that you don't use that same subset that's going to be changed every single time. Okay, so once you do that, that would be like your solution testing or like your termination case. And then, yeah, okay. But yeah, then we just, I think we could just create like a temp array and then like add it. Actually, for this one, even a copy of it seemed to work. So, okay. Great. This is for like the solution testing part, like we were saying. Next, what do we do next? We're talking about the two decisions, like we either take it or we don't, right? So if you take that particular number at that index, which is if you're here, like if you're at 1, if you take it, then you append it into your current subset and then you run backtrack with it. And what does that mean? It basically means visiting the other ones. And when you visit the other ones, you'd again come into, if you go for, when you take that one and you go into the other iterations, it means taking one. Like now you're in the other iteration where you either take 2 or don't take 2, right? If you take 2, you're in the last iteration where you either take 3 or don't take 3. So this is all like iterations within iterations. So yeah, so that's what run backtrack with it means. And then we also have to simulate the case where we don't take it. So that means we can remove whatever we appended. So initially, if we append 1, you can remove it, and then that wouldn't, like, yeah, if you remove it, it wouldn't be in your current solution set, current subset. And then you can run backtrack with it again for the rest of it, like 2 and 3. Like what happens when you leave 1 and take 2 and 3, that kind of thing. So that's exactly what I've like written down here, like going through the iterations. So far, this is just the and at the end you just return subsets. right? You just return your solution at the end outside of the backtrack, right? Because subsets gets populated throughout backtrack, throughout the duration of backtrack, and until you visited all of these numbers here. Okay, so what is your base? Like, what does it look like before it even goes into backtrack? Your subsets would be empty, and then your current integer would be 0, and then your actual current subset that would also be empty. And then these are your initial conditions, right? The current index and the subset, they look like this. And this is what you're going to be passing into your backtrack function to call it from the main function. So because we are, I'm just gonna write it down here. Well, okay, I'm just gonna mention it like this. We know that it's 1, 2, 3, 0, 1, 2. That's the max. If your current index becomes 3, it will come out, it will drop out of your iteration. So that's where you begin. Okay, so you're beginning at 0. And what number is at 0? Here you have 1, right? So what do we do now? You have 2 decisions again. You either take it or leave it. I've written down these things because like it would help with like talking about them. So let's take it, right? Like if you simulate taking 1, then what do you do first? We spoke about if you're taking something, you append it to your current subset. You append it to your current subset, and then you run backtrack on it, right? So your current subset before all of this was empty. So you're taking 1, so you're adding that 1 to your current subset, and then you're going to run backtrack with your current index incremented by 1, which means your current index changed from 0 to 1. And at 1, your, just gonna move back here, at 1, your number would be 2, right? So again, you're at 2, you have 2 decisions, either take it or leave it. What happens if you take it? And you still have not, you haven't really finished the, you haven't finished the whole like leaving 1 case, because you're still in the backtrack, like you're still within one of the iterations when you took 1, right? So you just took 2 now, right? And you're going to see what's going to happen next. So your subset before you took 2, like you appended 2 to your current subset. You're going to do that now. Like you're going to take 2, you're going to append it to your current subset, and then you're going to run backtrack again. And now what happens, right? Like your index, your current index was 1. Yeah, your current index was 1. Then you're incrementing it by 1, it becomes 2, right? So now, where would you be at? You would be here. You would be at 3, right? Okay, so now what happens? You're at 3. You have 2 decisions. You either take it or leave it. So you're taking 3 because that's what we're simulating first, right? You're taking it. When you say taking it, you're appending it to your current subset. Okay, so you would already append it to it. Okay, and then you would run backtrack again with that current subset. You would pass in, you would increment your current index by 1, right? And then, yeah, so now your current index is 3. And because we still haven't hit that like termination situation, we're going to we're going to get there now, well, because you've incremented by 3, and then you would, when you do this iteration, you'd hit this base case where your current index is greater than or equal to the length of your nums, right? It is, and so we're going to take whatever current subset you have, you're going to make a copy of it, and then you're going to append it to your subsets, like your actual like result set, right? You're going to append it to that, and then you're going to return, right? So far what we've done is we're in that taking 1, taking 2, taking 3, this kind of thing. Now we have to unpack leaving 3 just for this, like just for taking 2 kind of situation, like this. Yeah, so taking 2 decision, right? Like for this, you have to simulate the same thing for like leaving 3. We did taking 3, and we're going to do leaving 3. So if you're going to leave 3, then you're going to pop out. You're going to pop that out from your. You're going to pop out the last thing from your current subset, because you know you're at 3 because it's just it's the current element you're at, and you've just come out from a backtracking like iteration. So you have like you append that current element into your current subset, and then you'll do that backtrack, and then you'll remove that current element from your current subset. So just like a pop, because that would be the last element you inserted. So if you just pop it out, you'll get this. Your current subset would look like 1, 2, because before this it was 1, 2, 3. But you already recorded it, right? You don't have to worry about it now. So now it's just 1, 2. And then now you're going to simulate this, like leaving it, what kinds of subsets do we end up with, right? So you run backtrack with current index incremented by 1. And if you noticed, when we had the decision to take 3 or leave 3, our current index was 2, because 0, 1, 2, right? Like it was 2. And then after we, like when we're leaving 3 again, we would increment it by 1. So that would, yeah, so that would lead us to our base case again, where 3 is greater than or equal to length of nums. Yes. So what we do is, what is our current subset at that point? 1, 2, make a copy of it, and then store it in subsets, and then return. So far, we've still if you get the pattern, like you're like at one point, I'm just gonna lose patience, but like I'm really hoping you get how we're doing this. So every single time, either take it or leave it, and then if you take it, you run backtrack with it by iterating through the rest of the array until you hit the base condition. And then you remove that same element, and then you do the same thing for the rest of your search space, which is nums. We did what did we do? Yeah, we did leaving 3. This is for taking 1, taking 2. For taking 2, we did taking 3 and leaving 3. Now we have to leave 2, right? And this is all for when you choose to take 1. So in here, we're going to have another case for leaving 2, right? So at this point, what would your current subset look like? It would have 1, 2, and 2 is the last element that was inserted before this. So that will get popped out. And then this is going to be your current subset. And now you're going to backtrack again. Here, your index was 1, current index was 1. Now it becomes 2, right? And once it becomes 2 again, that means you land, you land here, you land at 3, right? So now what do we do? You landed the number 3, the index 2, okay? Should have really changed the numbers there. So what do we do again? 2 decisions, either take it or leave it. Take 3 or leave 3. Like I didn't write out the entire steps, but like it's the same thing. Whatever happened here, like when you take 3, you add 3 to whatever subset you had at that time, and then you run backtrack, you increment by 1, and then again you'd hit the base case, and then at that point you'd be like, oh, okay, like I need to add this to my subsets, to my already existing subsets, right? And then I would return. And then I would do the same thing for leaving 3. And then, yeah, that's basically what I've written here. And these 2 subsets are generated with that. So I'm just going to store all this in our subsets. Let's see. Okay. We're just going to leave it here. Right. So this is what our subset looks like when trying to type and talk. I'm not good at that, but when you took 1 and then you took 2 and then you took and left 3 and then you left 2 and then you took and left 3 again. So these are all the subsets that you were able to get until then. So yeah, so now we're still at that, oh, now I just took 1, now I have to leave 1 and then do the same thing, right? So when you leave 1, then what happens? Then you would sort of be left with this empty set, right? Because you only had, at the time of like adding 1, you just had that number 1 into your current subset, right? So now you would remove that, right? And then you would run backtrack again. So when you had 1, your current index was 0, right? Now your current index, when you run backtrack, with this empty set and then your current index, it becomes 1 now. So now you'd land at 2. And again, for leaving 1, you're going to consider taking 2 and leaving 2. If you take 2 again, you'll have taking 3 and then leaving 3. And then again, if your index goes out of bounds, you'll have to like record these subsets that you see. You'd record it to your solution set. And then the same thing here. Like when you take, like, because you start off with an empty set, when you take 2, this is what your solution is going to look like. I mean, your current subset is going to look like. And then when you take 3, at the end, you'd be left with this. And then when you leave 3 and all of those other iterations after that, I think that there's just one. There's that base case iteration. Then you'd end up with this one. And then for leaving 1, you finish taking 2. Now you have to leave 2. And these would be the iterations for that. And when you notice, this is really cool, right? Like it's really intuitive, because this is like this leaving 3, this particular one, this is like the intersection of leaving 1, leaving 2, right? Leaving 2 and leaving 3. So like it is the empty subset that we were talking about, right? The 2 decisions, it lands us at the empty subset at the end. So after all of this, we would hopefully have all of our subsets that we want. Where was that again? Yeah, okay. So we had 1, and then when like we're going to just add these subsets. So we had 2, 3, and 2, right? So we do 2, 3, and then 2, and then we have 3, and then our empty subsets. So empty subset. So we have 1, 2, 3, 4, 5, 6, 7, 8, right? So this, I counted this because this would be helpful for us to understand our time and space complexity. Because like from this you can, because we have like 8 combinations, right? I've also written that down, I think. Yeah, so we have like our subsets have 8 combinations. 8. The length of our subsets array, our finished subsets array, is 8. So yeah, so we have 8, which is like, if you actually think about it, it's 2 cube, and which actually makes sense to equate it to like 2 power n. And why are we specifically mentioning 2? Because at every number that we're at, we have two decisions: you either take it or leave it. So when you generalize this, like you see that the number of subsets that you have is at max of 2 power n. But we also need to remember that at every recursion length, like when do we know that this is it, like this is where we stop, right? We know that when our current index reaches the end of the array, which like the end of the input array length of nums, right? So in this case, length of nums is 3. So we went until that end, which means that I'm gonna say at every recursion length, we're gonna recursion level, we're gonna check that and end it. So the maximum length that our subset can be is n. So that would be, so our overall time would be, oh, okay. What did I do? Yeah, so our overall time is going to be like 2 power n times n. I definitely feel like I could explain this better. So if you have like follow-up questions, like either ask it on the channel or here. But basically it's the number of subsets and the length of each subset, like the worst case length. So this is going to be your time complexity. And then I think I also spoke about the fact that at every turn, we're going to store a worst case of, length of nums, right? So that is going to be our space as well. And the recursion depth, it keeps going on and on, right? Like the recursions, like the call stack length, I personally feel like it should still be like 2 power n times n, like even the space. But like I've seen in some solutions and like people talking that it's like O of n, and I think this is why they say that. But I'm gonna like take the space explanation with a grain of salt here, because like in my view, this is how I feel about it. And I would also go as far as to say that it could also be whatever was the time complexity, but yeah. So with that, I think we're ready to like actually code this out. Like the coding part is like really, it doesn't take too much of time. It isn't like super involved, but like the actual like how do we get to that kind of part? And like sometimes you can't just do all iterations in a recursive kind of situation. You just have to trust that it works and it'll work. So if you think we're good to start coding, like please add like a thumbs up or a B in chat so that we can start. Awesome. Thank you so much, everybody. Okay, so what should we first talk about, right? We were talking about what if like nums is like empty or something like that. What happens then? So let's take care of that. If the length of nums is lesser than or equal to 0, you're welcome. If it's lesser than or equal to 0, you just return a empty subset kind of situation. But LeetCode wouldn't even like get into this because they've mentioned in the constraints that it's 1 and beyond. You start with 1 and like that's where the length of nums is. But like it's really good to like clarify this with your interviewer, if you're interviewing as well, to like what should we do in such cases? Is this case even possible? It's good to get these things out, because you'd end up with pretty weird bugs from prod later on. Okay, So once this is done, what should we do next, right? Like this is our result set, like this is what we're creating. And then let's actually write our backtrack function somewhere here. So let's just call, we need to have the results, and then we need to have like a couple of like base cases that we're gonna send in, right? So one thing that we would want is to keep track of that index, right? Like it's going to be incrementing every time. So that's that. And then you also need to remember your current subset, like you need to remember what the current subset is for each turn. So just those two are enough. And then you just write out your backtrack function. And this is going to be your current index, and then the other one is going to be your current subset. And now what do we write about? We write about our base case, right? And our solution termination, that case. And then we're going to talk about, decision to take that particular element, right? Current element. I don't know how to, yeah, I'm gonna do this. And then if you take that, then you have to append it, and then you have to run backtrack on it. Okay, and now we're going to leave your current element. So you'd pop it out and then run backtrack on it again, right? So, okay, this part, oh, and I forgot to, like before, like when we call it, it's good practice to just return whatever our solution set is, so that we don't forget later on and end up with embarrassing issues. So if what is our base case, right? Like if the length of, if your current index is greater than or equal to the length of your nums, you could do you could also create that copy, that deep copy, or you could do num for num in your current subset, right? You could have this, and then you could I think it's extend, right? I just did like a copy, and that seemed to work as well for some reason now. I think, no, it's not extend, it's just append. Okay, and then if we're going to do this, what do we do, right? We're going to take our current subset and append our current number, current element. So that is nums of the current index you're at, or current position that you're at. You're going to append it to your current subset, and then you're going to run backtrack on it again. This time you're going to increment your current index by 1, and you're going to increment your current subset. You're going to just pass in your current subset because you've already done the appending over here. And then here, what is the other thing, right? So you're going to pop it out, and oh, weird. And then you're going to call backtrack on it again. And this time you're going to again increment it and then pass. You're going to increment the index and then pass in your current subset. Ooh, okay. I think with that, we're kind of done with the code, because we were talking, I think the most time we spent here was just like looking at all of those different iterations and stuff like that. And yeah, so let's just run it, right? Like what was in our main, we had these things, like we had 1, 2, 3, 1, 2, 1, and 0. I hope it works. That's what's going on. That's weird. Show me more. Huh. Okay, I'm gonna get to this again. What did I mess up here? It's greater than or equal to the length of your nums. You just, which line do we have it in? Okay. Oh, that's so weird. I forgot to return here. So once you, because like the current index, it's just like you just append it and you don't really do anything, right? So yeah, that worked. Ooh, okay. So these were, when you go back to your main, right? You had 1, 2, 3, and for those you're gonna have 1, 2, 3, 1, 2, 1, 3, 1, like the same thing that we were discussing before. And then for this one, for 1, 2, we had 1, 2, 1, 2, and then the empty set. And then for 1, you just have itself and the empty set. For 0, you just have itself and the empty set. Okay, so that's our whole subsets discussion, going quickly because you've been really, really patient in listening to me like ramble on. So I'm gonna keep it short. The next steps from here, definitely look through this problem called word search, letter combinations of a phone number, and then all of these. I think they're like subsets 2, subsets 3. I'm not sure, but there are many other subsets kind of problems. And each of these problems are a variation for the initial one where they add in more constraints. Like for example, in this, and maybe in the next one, they're going to talk about, it should be in order. Like we don't accept out of order ones and, like the solution set, something like that. So it's worth looking at. And then permutations, that problem, I've linked these two. And then for the subsets, you've already seen the link, just follow from there. And then, yeah, like these are other different problems that you can work on from here. And we're already like super late, but if you have like other questions or something like that, tag me in the channel because I tend to forget sometimes. So please tag me in the channel, tag us, tag Karen, tag everybody in our team to like, so that we can get back to you on that. And then these are some other like useful links, like Karen was mentioning, like the repo, the GitHub repo, and then the REPL link, and then PRAMP is a good. I think they come under Exponent now. Like I think they changed their, like they were like separate before. I haven't gone over easy level ones, but if you feel like we should, I think somebody was already mentioning in the channel, but we took a long break, our team. So we're probably gonna get to that, like practice problems and stuff. Karen, like, do you remember, like I think Ina was mentioning it. So we should probably like get to that. So maybe we can cover.
I think I did do that as well. I think like, oh, let's do this. Like,
Yeah.
but then it's like, oh, it's the holiday. It's okay. Let's take a break. Let's take a break. But yeah, we have something like that in mind, Rosa. But like, because it would be a little heavy if like we take on like both series at once. So like, the earliest we would do probably like, let's just enjoy the series first and then see if like we can come up something. But if you have the idea, feel free to tag us, like Chen said, to let us know what you think. Like, you have any like suggestions, like feel free to let us know. We do want you to enjoy it. So let's wait for their, well, first of all, thank you very much, Chandler, for the amazing walkthrough. For those of you who just joined in on kind of like what is going on, why there's so little code, just a little breakthrough, just a little breakdown. The code itself is actually very straightforward. But the problem is, if you don't understand the problem and you don't know how to go through the solution, you will never be able to write the code. So that's exactly what Chethana is walking us through, how to think of the problem, how to tackle it, how to, find a way to solve it. The logic behind it is the key to solve the problem. So that's how we go through here. If we just showing you the solution, it will be like, if you very familiar with Python, like you'd be like, okay, this, okay, click, 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 okay, this. But then doesn't mean if we give you next problem and you'll be able to solve it. So that's the style. That's why Channel spends so much time to explain, like walk through everything. And we think with the logic here. So yeah, I personally, I try my best to learn catch up with that. But like we appreciate that. So in case this is like, if no one has any question and this is the first time you're joining, please follow us on Slack and social media. So we have a lot of exciting series going on. Please join them. We are a fun group. You will learn a lot from us, and we always open to questions, suggestions. Feel free to reach out to us, and just remember to join the Slack, and you can start from there. Yep, there we go. Yeah, thank you, everyone. Sheldon, any suggestions? Any last minute you want to share? Anything you want to share?
Well, yeah, like the usual, just with LeetCode and like with like problem solving, things can get super demotivating many times, but just go with it. Like, even if you're solving just like one problem per day, like if you're starting with easy ones, go with that. If you are stuck at a problem and you have no way of like getting to the solution, like you can't even see it, it's so far away that it's like in another continent or something. That time, just if based on what kind of problem you're looking at, if you're doing like medium problem, maybe give yourself, you would know, right? Like if you tell yourself, okay, I'm going to give myself 30 minutes, and then if I have nothing, like zero, then I'm going to see how it's done so that I can collect that tool or method of how it's done and keep it in my arsenal. So the next time I see something like that, I'll be like, okay, well, I did it like that the last time, the hard way. So I'm gonna, continue doing it like that. So never feel that, oh my, like, there's that thing where we always feel like, oh man, like, I don't know this. I can't do it. Like when you don't know it, then our best bet is to learn it and then like see if we can figure that pattern out the next time we see something super similar to it. So that's all the thoughts I had, because we're coming back after a long time to study group, like a month. Just wanted to talk about that once more.
Yeah, I agree. All right. About time. Thank you for joining us.
Thank you.
And we will see you guys next 2 weeks in the next group. Yes.
Awesome. Thanks, everybody.
Thank you.